It is a great pleasure to introduce you Jorge Lauret from FAMAF, Universidad Nacional de Córdoba. Jorge made his PhD in Córdoba, and he now is a professor there and a researcher of CONICET. He has a lot of interesting works in very prestigious journals, and we are delighted today to have him here to speak on the stability of compact homogeneous Einstein manifolds. Thank you, Jorge.
Okay, thank you, Gaston, for the introduction. And well, thank you to the scientific committee for the invitation. I'm really glad to have the opportunity to give a talk in such an important congress. Okay, so I will speak on some Riemannian geometry. It's a joint work with Emilio Lauret and Cynthia Will. And maybe we may start with some, I don't know, 5 minutes course on Riemannian geometry. So we have a differentiable manifold, smooth manifold. And one may think that a smooth manifold is like, well, I don't know, a topological space where you can do some calculus. But actually, to do some analysis, I mean, as a generalization of Rn, but is the fact is that one uses much more from the Euclidean space to do analysis than the topology, right? So what you really need to do something is called a Riemannian metric. A Riemannian metric is just to have, I don't know, a choice of an inner product on each tangent space in a smooth way, of course. And so you can measure the length of tangent vectors and angles, right? But it's amazing all the other consequences of having this choice. I mean, you now know how to measure the length of curves, and so you have automatically a distance. So you have a metric space now by defining like here, very natural, in a very natural way. But also much more. I mean, you also have a notion of area, of volume. You can now talk about the gradient of functions. All things that you are in Rn, in the Euclidean space. I mean, you do this without noticing that you are using this inner product on each tangent space, okay, that you have naturally on Rn. And more importantly, you have a canonical connection. So it's a canonical way to connect two different tangent spaces, which gives you the notion of parallelism, of geodesics, and holonomy, and etc. And maybe the most important concept is curvature. Is the curvature you get from a Riemannian metric really provides a shape to this topological space M, to this manifold M. Okay, so that's a Riemannian metric. And so let's talk about a little more about curvature. You must remember what the Gauss curvature is of a surface. And you took these sections, and by just computing the curvature of the curves of these plane curves, which are the intersection, you take the minimum and the maximum and multiply them and get a number called the Gauss curvature, which, okay, so this is negative curvature, like a neck. This is positive curvature, like a sphere. And this is zero, flat, zero curvature, like a plane or a cylinder, because you are multiplying the two principal directions. So that's the curvature of a surface when you are in dimension 2. But well, here we are in dimension n. Okay, so it's more complicated. So for each point of the manifold and for each plane, you have this number, which is the Gauss curvature of the surface generated with geodesics, if you want. Geodesics with starting with velocities in the plane. And so why is more complicated? Well, because now you have to choose a whole Grassmannian, the space of 4 planes in an n-dimensional vector space. This is a huge space, and well, that's called the sectional curvature, and is equivalent to have this 4 tensor defined with the connection. Okay, it's a very complicated object. So when you have a Riemannian manifold, okay, you have this sectional curvature or the Riemann curvature operator, and then since they are very involved, you want to average, okay, to get other notions of curvature. I mean, maybe you're losing information, but you can do something. The first averaging is the Ricci tensor, is a bilinear symmetric map, and is defined for each direction x in this way. You complete to an orthonormal basis and take the sum of all these n minus 1 planes containing x. Okay, and that's Ricci curvature. And scalar curvature is to average again. So now at each point you get the number. This would be Gauss curvature in the 2-dimensional case. Is the sum of all is the trace actually of the Ricci tensor with respect to the metric. Okay, but okay, so scalar curvature is a function on M. Okay. Okay, so this is a natural question. Given a manifold, if there is a canonical Riemannian metric on M, okay, a most distinguished, and well, there is a book called, best book, a classical book called Einstein Manifold, which, well, it's like, I don't know, 800 pages dedicated completely to Einstein metrics, in a way to try to propose Einstein metric with as very nice metrics on M. Okay, so what you have is a compact. In the whole talk, M will be compact, And consider this invariant of M, which is the space of all Riemannian metrics on M. Okay, it's a huge space. You consider all Riemannian metrics together in the same set. Is an open cone in this fiber bundle, which is this is a vector space, but infinite dimensional vector space, which is the vector space of all symmetric two tensors. Is to choose a symmetric bilinear form on each point. So that gives you a vector space, and well, Riemannian metrics is a subset such that at each point this bilinear form is positive definite. Okay, it's an inner product, so it's not that bad. It's an open subset of an infinite dimensional vector space. It's an infinite dimensional manifold, if you want. It's a very interesting invariant of the manifold M. I mean, the existence of elements here with certain, for instance, curvature properties can give you a lot of information on the topology of M. Okay, that's the way the Poincaré conjecture was proved by Perelman using the Hamilton-Ricci flow, for example. So, in the search for distinguished metrics, Hilbert, more than 100 years ago, considered this functional on the space M of all Riemannian metrics. It's called the scalar curvature functional because it's to assign to each metric the integral of the function scalar curvature. So it's the assignation to each metric you assign a number. Okay, it's a function on the space F M of all metrics. Okay, so a natural way then to find distinguished element is to ask about critical points of such a natural function. Right? It's the simplest curvature functional you may consider. So we have to restrict to the volume 1 metrics because otherwise it is homogeneous, this function, and then you're not getting any critical point. And well, Hilbert proved that this was kind of independently from general relativity, independent of Einstein, right? So this is the way Einstein metrics were born in mathematics. So G is a critical point of this such a natural functional if and only if the Ricci tensor is a multiple of the metric. Okay. Or in other words, is the Ricci curvature is constant. Okay. So in each direction that you take this average, you get the same number. So because constant sectional curvature is too strong. But okay, so these are Einstein metrics, and well, here you have this book. Okay, so once you have that these critical points. Oh, by the way, you can ask whenever you want any question. So then you may ask, what about what kind of critical point? Can you have local maximum, local minimum, and okay, then you take the tangent space of this space of metrics, remember that this is open here, so the tangent space is this vector space, and it turns out that the space decomposing in this way, where this first summand is are called the trivial variation, because it's the tangent space of all the metrics which are isometric to G. So pulled back by diffeomorphism, you get different metrics, but they are all geometrically equivalent. Okay. So that summand is irrelevant. Then you have these conformal variations. And then finally you have this subspace called the TT tensors, which is the relevant subspace to consider. So take the Hessian or second derivative defined as in calculus of the functional, and then ask for the signature. If it is positive definite, then you will get a local minimum, etc. Okay, that's the problem. So it's a calculus problem, but in an infinite dimensional space. Okay, why this is relevant? Because, well, the decomposition is orthogonal with respect to the Hessian, is 0 clearly on these trivial variations, is positive on conformal variations, and is in this third, in these TT tensors, is the nullity and the co-index are finite on this subspace. So it's mostly negative, but it can be 0 or positive in a finite dimensional subspace. This was discovered by Coiso and Berger. It's kind of a miracle. And then this is the right subspace to analyze the stability of the function. Okay. The subspace is precisely the tangent space of this very natural subspace of metrics, which are the metrics of constant scalar curvature. When this function, which is actually a number at each point of the manifold, is a constant function. So are the metrics such that the scalar curvature is just a number, one number. And so you have that we will be studying the co-index of the functional restricted to this space. Okay. So the question is, when is negative definite? That is, you get a local maximum for the functional restricted to this constant scalar curvature metrics. These are called stable. Okay. Unstable is when you have a positive direction for the Hessian, so you have a saddle point, and degenerate when you have something in the kernel of the Hessian, as always. So these are the kinds of Einstein metric you may get. Okay, so to the Hessian, a formula for this Hessian that we have to study, the eigenvalues, is this, where this delta L is the Lignerowicz Laplacian. It's a very complicated operator. As you see, the definition involves the Riemann curvature tensor, the Ricci tensor, but okay, it doesn't matter. It's known for just a few metrics completely. And well, since you have this formula here for the Hessian, 2 rho, okay, recall that rho is the Einstein constant, is called. Then if you take the smallest eigenvalue of this Lignerovich Laplacian, you get these equivalences for the stability, instability, and degeneracy. Okay, is that the 2 rho is less than this first eigenvalue of the Lignerovich Laplacian, which may be negative, it's not necessarily positive. Okay, so for symmetric spaces, which are in a sense the most beautiful Riemannian manifolds, the most famous, you get that they are all stable, okay, with some exceptions. These exceptions, these are the groups you all know. These are group of matrices. We will talk in a minute about this. These are called homogeneous spaces. Are all Lie groups. Well, these are unstable, and these other ones are degenerate. And we don't know if in this case, in this degenerate case, I mean, you have the same problem as in calculus. When the Hessian is non-positive, it's like you cannot conclude that whether it's a local maxima or maximum or not, right? It's the same thing. Well, we don't know except for this SU3 in dimension 8 and this SU2n over SPn, which is here. Only for these two degenerate symmetric spaces, we know that it's not a local maximum. It's open for the rest. And it is also open if there are any other stable Einstein metric other than these symmetric spaces, always with positive scalar curvature. But this is incredible that this is still open. I mean, it may be the case that only symmetric spaces are stable. But okay, this is open. Okay, so this is a second part of the talk. You can come back if you're lost with too much Riemannian geometry. We can talk now with more algebra. So what are Lie groups? A Lie group is at the same time a manifold and a group. Okay, so you may ask what would be the connection between smoothness and groups, but yeah, is of course with these compatibilities, right? That the product and inverse functions are smooth. So that's a Lie group. And well, actually is one of the deepest connections in mathematics, maybe. Smoothness with groups. As an example, you may always think in a closed subgroup of matrices. So as you see, this is kind of a miracle too, right? I mean, just you have only a closed subset, but since it's also a subgroup, it's automatically smooth. It's really incredible. And not only it's smooth, it's a submanifold with the Euclidean topology, with the relative topology from GLNR, which is an open set in a vector space. And this example is much more than an example, actually. Most Lie groups are of this form. And so in a group, in a Lie group, it's very easy to put a Riemannian metric, because any inner product, you can take any inner product on the tangent space of the Lie group at the identity and walk around it, the group G, with left translations. And so you get what is called a left invariant metric on the Lie group. Okay. The tangent space at the identity is called the Lie algebra of the Lie group, and is a subalgebra of matrices in this case. A subalgebra with respect to the Lie bracket of matrices. Okay. AB minus BA. So that's also incredible. Okay. On the other hand, we have also this other miracle, which are homogeneous spaces. You take a Lie group G and any closed subgroup of G, K, and then the quotient now, the coset space, admits a natural differentiable structure. It's a manifold. And these are called homogeneous spaces. And well, the way to put some geometry in a homogeneous space is similar. You just need an inner product on the tangent space of M, which is now the quotient G over K of the Lie algebras, and ask for this inner product to be add K invariant, where this add is the adjoint representation, this is conjugation. Okay, so we have in this situation, the homogeneous is a mix between geometry and algebra, and so of course promises a very nice interplay. So take a compact homogeneous manifold. A homogeneous manifold is a manifold where some Lie group is acting transitively. Okay, and we fix a Lie group G acting transitively on M, and also we fix the action, because everything is kind of complicated. It's the same manifold can admit action of very many different Lie groups, but also the Lie group can act on the same manifold in different ways. So what we are fixing here is M, G, and the action of G on M. That would be our setting. And so we now consider the Riemannian metrics on M, but which are G invariant. Okay, such that G acts by isometries on the corresponding Riemannian manifold. Okay. Okay, so this MG is now a finite dimensional vector space. Sorry, a manifold, but the finite dimensional manifold in this is open in this finite dimensional vector space. The dimension is here. So we have the same problem as in the general case, in the classical case, but now everything is finite dimensional. We have this scalar curvature functional. The gradient is precisely the Ricci tensor, and then we have the same. G is Einstein if and only if it's a critical point of this functional scalar curvature. And so a natural question is to study now what we call the G stability of Einstein metrics. So what type of critical point is an Einstein metric as a critical point of the functional on this finite dimensional manifold. So that's the question we are studying. And so, well, we first have this lemma, which is what is the tangent space, to apply now the Hessian. And we have this, that what we get is just, you take now the G invariant TT tensors, and then the orthogonal complement is just these are trivial variations now, but of course you cannot act with any diffeomorphism. To get again a G invariant metric, you act with this very special group of diffeomorphism of the homogeneous space, are the automorphism of G taking K to K. So we can naturally define G stability, G instability, and G degenerate in the same way. Okay. So this will imply, for instance, G stable, it will be a local maximum of the functional scalar curvature on M1G, and so on. Okay, so let me show you why to study this or to get anything about this G stability is kind of a win-win situation, because if you get that one of these homogeneous metrics, these are very, I don't know, algebraic Riemannian metrics if you want, is G unstable with algebraic methods, you get this, but then it's also unstable in the classical case, because what you got is one of these T, which is G invariant, but it's also a TT tensor, so you can use that T to prove the same instability as in the classical case. And then by result of Krohnke and Kauhe, you also get this Ricci flow dynamically instability. And it's very interesting. This Ricci flow is a famous curvature flow. As I say, introduced by Hamilton, studied and used by Perelman to prove Poincaré and uniformization conjecture. And so this instability means that you can, there are metrics as close as you want from G, such that if you run the Ricci flow, they go away. And also, you know that G does not realize the Yamaha invariant by results by Bohm, Wang, and Siller. Okay, if you get that is G stable, then it's a local maximum, and these metrics are really jewels. Are very, very difficult to find. Is extremely strong condition already in the G stable case, because these will be the candidates to be non-symmetric stable Einstein metrics, right? In the general case. But in this G invariant case, it's also very, very difficult to find this kind of metrics. Okay, and if you are able to prove that is G non-degenerate, so the Hessian is non-degenerate on this G invariant situation, then what you get that G is rigid, which means that is isolated in the set of all Einstein metrics. Is the unique one up to isometry in a neighborhood. And this is related with this. This is maybe one of the most important questions in this topic. We don't know yet if, given a homogeneous space, if you always have only finitely many Einstein metrics, G invariant Einstein metrics, up to isometry, of course. We don't know. This is open, and as you see, I mean, if they are finite, if and only if they are all rigid, right? Because what we know is that this space is compact. So that was proved also by Bohm, Wang, and Siller. Okay.
Jorge.
Sí. Yes.
Do you know the answers for this question for some groups G? Or you don't attack the problem like this for looking for some groups?
No. There are. I mean, the space of homogeneous spaces is really overwhelming. I mean, but yeah, you know, by computing explicitly for many cases that there are only finitely many. Yeah. Okay. But there is no any like general result. Yes.
Thank you.
We will see some examples in a minute. For large families of homogeneous spaces, you know, is finite. Okay, so what time is it? So the Ricci curvature in this G invariant case, as expected, a formula, you can give a formula for the Ricci operator in algebraic terms, okay? And the formula is as follows. You take, this is called a reductive decomposition. So now this P is the tangent space of M at the origin point, so the class of the identity, and take a G invariant metric. Denote by mu the Lie bracket of G, of the Lie algebra G, and restrict and project mu on P. So you now have a bracket, a bilinear skew symmetric form on P with values in P. And so the formula for Ricci is, it has two parts. B mu is the Killing form. It's a very algebraic object associated to the Lie algebra, the Killing form. And this M is defined like this, where theta is this representation. Okay, but it turns out that it's precisely the moment map from geometric invariant theory for this representation. This is M mu P. Okay, so you are finding here not only Lie theoretical properties and tools, but also from geometric invariant theory. Okay, and so, well, of course, a lot of representation theory and algebra can be used to study the geometry of these metrics. Okay, so this is Ricci, the moment map minus the Killing form. And so what about the Lignerovich Laplacian, which is essentially the Hessian? So we were able to prove that a formula for the Lignerovich Laplacian, delta L, in terms of an operator LP, this sim of P are symmetric operators of P. And so LP is defined also in terms of the representation theta, which is the representation, the usual representation of GLP on this space of all Lie brackets, and the moment map. Okay, but this formula is very complicated. In the naturally reductive case, simplifies a little bit, and so we were able to do something. But so let me give what we found is a formula to compute this Lignerovich Laplacian in terms of known data. So the same as in the general case, if you take lambda p the minimum eigenvalue of LP, then you have these equivalencies, right? I mean that the metric will be G stable if and only if 2 rho, so 2 times the Einstein constant, is less than this lambda p, and in that case you get this that is a very special local max for the scalar curvature, no? And otherwise you get G unstable. And if 2 rho is in the spectrum of LP, you get that the Hessian is degenerate, and then you cannot conclude if it is a saddle or not. But then it's very important to compute this lambda p and this the spectrum of LP. We are in, recall that we are in a finite dimensional situation, so but before that, for instance, you have something for free. If you take the Killing left invariant metric on a compact simple Lie group, so minus the Killing form, since the Killing form is negative definite, minus the Killing form defines a very, very canonical metric on a simple group G, okay? And is always Einstein. And well, in this case, this operator LP is precisely the Casimir operator of this representation symmetric of G, sim of G of G. Okay, it's not irreducible. It has 3, 4 summands, irreducible summands, and then, but on each summand, the Casimir operator is a multiple of the identity. So it is easy to get the what is lambda p, and then you get more or less for free what's the stability type of this very natural metric on a compact simple Lie group. You get this. So it's always G stable because these are all symmetric spaces. But okay, they are all G stable, and you get only for SUN and SPN travels. I mean, bad travel. In SPN is unstable because this is less than 1/2, and 2 rho is 1/2. And in the SUN case, you get this degenerate, and you cannot conclude if it is a local maximum or not. And in the exceptional case, they are all G stable. Okay, that's for free. But let's go to a general situation. So what you do to study in homogeneous geometry, you usually fix a bi-invariant metric Q on the Lie algebra, and then take the orthogonal decomposition as a reductive decomposition and the structural constants of the Lie bracket of G, restricted to P. Okay, these are just, you are measuring the Lie bracket on Pi times Pj projected on Pk. Okay, so these numbers have been used for decades, since Wang and Siller introduced them to study Einstein metrics. And then this decomposition P1 plus PR, if you decompose P as in irreducible subspaces for the representation of for the adjoint representation, then this will be an add K invariant inner product for any positive numbers you take, x1, xr, okay? So the choice of these R positive numbers gives you a G invariant metric. And this is just to show that the Einstein equation for a G invariant metric, which will be this, that all the Ricci eigenvalues be equal to rho, is in terms of these structural constants and the metric x1, xr. So in the literature, there are, I would say, hundreds of papers studying in different situations for different homogeneous spaces, studying Einstein metrics, and so they all use these numbers to compute this. IJKs is not so easy, but they are available in the literature in many cases. So what we did is to try to find a formula for this Lignerovich Laplacian in terms of these numbers and the metric. And this is the formula. Okay, is complicated, but okay, with a computer, if you have these numbers, you can compute the spectrum of this LP and study G stability. Okay, so we did that. For instance, when G is semi-simple, you also have like the Killing metric for a compact simple Lie group. When G is semi-simple, for any homogeneous space G over K, you have like a canonical G invariant metric. It's called standard and is the one given by the Killing form. Again, it's very natural because, I mean, anyone who study the algebras must like a lot the Killing form, right? It's so useful. Is non-degenerative and only if the algebra is semi-simple and so on. And so this is a very, very canonical Einstein metric. But curiously, they are not Einstein. They are not all Einstein. So a classification in the 80s, this was really a breakthrough in the field. It's a paper you can imagine full of representation theory to classify which of these standard metrics are Einstein. They obtained 12 infinite families, some of them complicated, huge families, and 22 isolated examples. The equivalence for being Einstein is that the Casimir operator is the same multiple on all the irreducible summations. Okay, so it's full of representation theory. And okay, so we can use that the formula to get this information. This is the first family of standard Einstein metrics. We were able to compute the smallest eigenvalue of LP and to get this information about what kind of critical point is this standard Einstein metric for these homogeneous spaces. The thing was that, I mean, these structural constants, IJK, were like very uniform in this case. And so the metrics of LP was essentially the adjoint metrics of a graph. And it was a more or less known graph. So in a book on graph theory, you can find which are the eigenvalues of that adjoint metrics attached to this graph. And the same for all these. This is the second family, the SPs. As you see, in many cases, they are all G unstable. So no joules in these families, all G unstable. But sometimes you get local minima. Very, very interesting. And finally, the SOs. This is the third family, and you get local minimum only in this case, but this is an infinite family too. Okay, with Emilio Lauret, we are working on the G stability and the Ricci flow stability, where also the Laplace-Beltrami operator, the usual Laplacian is involved, the first eigenvalue of the usual Laplacian, to study the stability of the rest of the standard metrics. Okay, so some more exploration we did with Cynthia is on this huge class of homogeneous spaces called generalized Wallach spaces. This is the definition. They are classified for G simple. They were classified by these people and also the Einstein metrics, but you get 5 infinite families and 10 exceptional examples, and each homogeneous space admits between 2 and 4 Einstein metrics. So it's really a huge class of Einstein metrics, homogeneous. And on the other hand, flag manifolds. Flag manifolds is when K is the centralizer of a torus. If it is a maximal torus of G, it's called full flag. And if these are not completely classified, and even in some of these flag manifold is open if there are only finitely many Einstein metrics or not, it's open. But if we assume that the second Betti number is 1, then they are classified. You get 13 spaces, each one admitting between 3 and 6 Einstein metrics. And this R, which is the number of P1 plus P2 plus PR, the number of irreducible summands in the isotropy representation, goes from 2 to 6. Here for Wallach is always 3. Okay, but that determines that determines the dimension, the dimension of the manifold where we have our functional. Okay, so these are some tables that you can look at with more time in the video. If you are you recording? Oh, okay.
Yes, we are recording. Don't worry.
Okay. Can see. These are some Wallach spaces. This is only the case where all the dimension of P1, P2, and P3 are the same. And well, we got this. We were able to compute lambda P and the other eigenvalue, the larger eigenvalue, and get, in this case, only this is a local max, but this GB, which is the standard metric actually on the Wallach spaces, so all these are in the list by Wang and Siller, is always a local minimum. And as you see, we get some zeros here. And well, I don't have time to say something about that, but this this implies that this Einstein metric is not, I mean, the Ricci map is not a local diffeomorphism at the metric G. Okay, and so there may be a curve of metrics through the Einstein metric with the Ricci tensor constant. So that's very important for a problem, a classical problem called the prescribed Ricci curvature problem. Okay, so well, these are the remaining Wallach spaces, and these are the flag manifolds. So to finish, well, here you have more eigenvalues. I'm showing just the case R equal to 4. In the paper, you can get all the tables. There are like more than 10 tables actually. These are only a few ones. When you get co-index 0 here, as you see, this is a Kähler metric, which is a local max, because co-index is 0. The co-index is where the Hessian is positive. So the Hessian is negative, and yes, you get local mass 2 for this Kähler Einstein matrix. And well, to finish, we have these remarks on the exploration. So the only joules we found were these ones, as I mentioned. So we support the expert think that of course that G instability is generic in the homogeneous case, in some sense. Well, we also have these other remarks. Let me choose one. Well, we said that for any, yeah, well, this is the remark about the prescribed Ricci curvature problem. But let me go to the last remark, which is related to general relativity. So there is this this generalization of the famous Schwarzschild black hole, which is, this is a 4-dimensional pseudo Riemannian metric with some properties, where you replace the two sphere with any compact Einstein manifold, Mn. And the thing that there is an instability concept here, and is also written in terms of the smallest eigenvalue of the Lignerovich Laplacian, and is this inequality. Okay. And then we read this paper and say, well, we have such a large amount of Einstein metric. Let's see when do we get this instability. But from all the Einstein metrics we studied, only this space, which is a full flag manifold, is SU3 over the maximal torus. Okay, so it's a 6-dimensional homogeneous space, very, very simple, very famous. This is the only one for which the inequality is satisfied by lambda p. But recall that lambda L is less or equal than lambda p. So if lambda p satisfies this, then you get instability for the black hole. And But okay, yeah, is the only one. So that was very curious for us, and I don't know if physicists may be interested in this situation, in this property. Okay. Thank you very much for your attention.
Thank you very much. We thank Jorge for a very nice talk. You may now turn on your camera and ask any question that you want to Jorge. I will stop recording.